Welcome back, my friends. We will continue our journey through the valley of the shadow of confidence intervals. Now, don't you just love this little quote that 98% of all statistics are made up? I just think that's really cute. So let's go back to what we were discussing with confidence intervals. Do you remember this little diagram? In this diagram, we were talking about taking a sample and determining from the sample, x bar and s of the sample, we know the number that we have in the sample, and using that to construct a confidence interval for the true value of the mean of the population, a value that we wouldn't know. And that confidence interval having a lower bounds and an upper bounds where we could establish a given level of confidence. For instance, it might be 99%, 98, 95, 90%, and so forth confidence that the true mean lies in this confidence interval based upon our sample and our sample mean and our standard deviation of the sample. Now here's the central limit theory. Now read through this and let's see what we can do with it. Given any distribution of sufficient size, any distribution, whether that distribution is normally distributed or not, if an infinite number of samples of size n are taken, infinite number of samples, we took sample 1, sample 2, sample 3, sample 4, sample 5, and we continue to take them forever, of size n, maybe there's 30 in the sample in each sample, maybe there's 50 and so forth. Given any distribution of sufficient size, if an infinite numbers of samples of size n are taken, the sample means x bar sub I, the x bar 1 for sample 1, x bar 2 for sample 2, so forth, going on to x bar infinity, will be normally distributed. The sample means will be normally distributed around mu with a standard deviation of s divided by the square root of n, where n is the number in the sample and s is the standard deviation of the sample. This is very profound. It says that around mu, if we take an infinite number of samples, that those sample means will be very tightly normally distributed around mu with a standard deviation of s divided by the square root of n. As the samples grow bigger, n gets larger, which means that this becomes a very smaller value, pushing them in on the sample mean mu. Now, two relevant values are important for constructing a confidence interval based upon sample size n. These are x bar, the mean of the sample, and s sub x bar. This is the standard deviation of the x bar distribution, and it is equal to the standard deviation of the sample divided by the square root of n, where n is the number in the sample. Now let's see if we can see some things about that. Suppose we have this distribution. It's a very large distribution. Obviously, it's a standard normal distribution, but each point we take samples, and here's where x bar 1 fell, x bar 2, x bar 3, x bar 4. You see, if you watch that just a minute, that the sample means are going to congregate very closely and very tightly around the distribution mean. That tells us that x bar is distributed around mu, and that being very tightly distributed around mu, it has a different standard deviation than does the distribution. Okay, each point in the mean each point is the mean of a sample of size n. Now, these cluster around mu, and this is the x bar distribution represented. Those cluster around mu, and they're normally distributed around mu, and they are very tightly clustered around mu. In other words, they have a smaller standard deviation than the standard deviation of the distribution. This is what the central limit theorem says. It says that if we take an infinite number of samples of size n, that the means of those samples will be normally distributed around the true mean with a small standard deviation equal to s divided by the square root of n. In other words, the larger the samples are, the more tightly they congregate around the true mean. Now, let's read that again. Given any distribution of sufficient size, if an infinite numbers of samples of size n are taken, the sample means x bar sub I will be normally distributed around mu with a standard deviation of s over the square root of n, where n is the number in the sample and s is the standard deviation of the sample. Two relevant values are important for constructing a confidence interval for mu based upon the sample of size n. These are x bar and finding s of x bar. And the standard deviation of that x bar distribution, which hovers very closely to mu, is s, the standard deviation of the sample, divided by the square root of n, where n is the number in the sample. So we have two values we will need to calculate, x bar and the standard deviation of the x bar distribution, which is calculated with this formula. Again, I want to thank you very much for your support. Don't give up. We're going to get through this material, we're going to master it, and we're going to do well. Now, instead of quoting the Hunger Games, I'll remind you of the old Star Trek show which says, "Live long and prosper," the old Vulcan greeting. And if you meet a Vulcan who says, "Live long and prosper," the answer is peace and long life. You have a great day.